Hello students. So in the earlier class we discussed about basics of a transformer. So transformer is a static device which transforms electrical energy from one circuit to another circuit without changing power and frequency. Okay, so that was the definition and introduction to transformer. It was a static device, so there are no rotational parts in transformer, and it transfers electrical energy from one circuit to another circuit. Okay, and there is no change in power and frequency from one circuit to another circuit, but there can be changes in voltage and currents such that power will be constant. So this was the basic idea about a transformer. Now let us see how a transformer really operates. Okay, so I have already told you transformer is excited with AC supply. So here we have given a single phase AC supply of 50 Hz frequency to the primary side of the transformer. This is primary side, right? And the other side is secondary. So primary is excited with AC supply. So as it is a closed circuit, there will be a flow of current in the primary. I1 is the current flowing through the primary. Okay, and this current will flow through the winding. So whenever AC current flows through a coil or inductor, I, okay, it is AC current. So this current will induce some flux in this coil, that is given as pi. Okay, so due to this pi, according to Faraday's law of electromagnetic induction, okay, whenever there is a rate of change of flux, there will be a EMF induced in that coil. Whenever there is a rate of change of flux in a coil, there will be a EMF induced in that coil. This is Faraday's first law. Okay, and Faraday's second law is saying the induced EMF is proportional to rate of change of flux linkage. So how much is the rate of change of flux is happening in a coil is proportional to EMF induced across the coil. The more is the rate of change of flux, the more will be the EMF induced in the coil. So combining these two equations, we can obtain the EMF equation in a transformer. Okay, so that we are going to see later. So till now we have a flux induced in the primary. Okay, so let us take a black pen. So I am taking direction of flux is upward. So here a flux has been induced in this coil. Okay, primary coil. Till now there is a flux in the coil, primary coil. So now what is happening here? This coil is wounded on a magnetic core. This red color square I have drawn is a magnetic core, that is I have written as core material. This is a magnetic material. So we have a flux on a magnetic material. Magnetic material has a property to allow the flux to flow through it. Okay, so this induced flux in the primary coil will flow through the magnetic material here, that is core material. So here you can see pi, the direction is right side, the flux direction is like this, and this flux will flow in this core material circularly, and this flux is same in the core material. So wherever we want to check the core flux will be same. Okay, so this flux induced in the primary coil is flowing in the core material, which is having the secondary coil also wound on it. Here you can see there is a secondary winding on the transformer second leg. This is called second leg, this is called first leg. On first leg we have mounted primary coil, on the second leg we have mounted secondary coil. So the flux from primary coil links with the secondary coil here. Okay, so initially there was a flux in primary coil, that is called self-induced, self-induction or self-inductance. Due to self-inductance there was a flux. Now this flux in the primary coil is cutting the secondary coil now. This is called mutual inductance. So due to the current in one coil, there is a flux in another coil. This is called mutual inductance. I think you can't see this. Okay, yes, now you can see, right? Okay, so this is mutual inductance. Okay, because of current in primary coil, there is a flux linkage in secondary coil. Due to this flux linkage happening in primary and secondary, there will be a EMF production in primary and secondary, which is denoted with yellow color. This is E1. E1 is induced EMF in primary coil, primary winding I can say, and E2 is induced EMF in secondary winding. Okay, so all these are AC in nature. Okay, all these are AC in nature, all are AC quantities. Okay, V1 is supply voltage, which is also AC. V2 is secondary voltage, secondary voltage at load terminal, secondary load voltage. Okay, so these are the parameters of transformer, and N1 N2 are turns. N1 is primary number of turns, N2 is secondary number of turns. Okay, so here we have two coils, two windings placed on a circular magnetic core. Okay, first one which is connected to the supply is called primary core, second one which is connected to the load is called secondary winding. Okay, now let us see how the EMF is being induced and what is the EMF equation here. Okay, so I told you, so let me draw the transformer again here. So here I have it, small transformer. Okay, now I have windings on primary and secondary. Okay, like this. So I have wounded two windings, primary and secondary. Now I am going to give AC supply to the primary. I have load connected on the secondary. Okay, now I am going to give AC supply, single phase AC supply of 50 H generally. Okay, so a voltage V1 is applied. So E1 will be induced in the primary coil, and there will be a flux production first. This flux will link with the secondary coil also. This flux linkage will induce some EMF E2, and this will cause some current I2 to flow when it is a closed circuit, and V2 is the voltage across load terminal. Right, this is what we have seen till now. So there is a current flowing in the primary, that is called I1. So I1 is current in primary winding, and what happens here is, so inductor or a coil needs some current to excite, to create flux here. So here the coil is being excited with some current and some flux is being created. Similarly, the primary winding in a transformer is like a coil, and it needs some of the portion of the input current as exciting current, that is called I. Okay, that means a coil needs excitation current. This current I mu is called excitation current to create flux. So here comes the reactive power concept in electrical engineering. Actually, this is reactive power consumption of inductor. Okay, so we don't need to learn it now. Okay, so basically any coil or any winding in a machine or a transformer needs some excitation current, that is given as I mu, generally I mu. So this I mu will be subtracted from this supply current. Okay, so this I mu will be taken from this supply current. Okay, so some portion of the I1 is being lost here just to generate flux. So it is not transferred to the secondary, it is just being created by the flux. Okay, I mu is excitation current. As we are giving AC current, this is also AC current. Okay, magnetization component of current for creating the flux in the core. This is magnetization component of current for creating flux in the core. This is just to create the flux in the core. Okay, so as it is AC, the value of I mu will be Im sin omega t. Im sin omega t. Okay, because it is AC current. Now there is a primary MMF induced in the primary winding due to this magnetizing component of current. Okay, Now there is a flux production due to this magnetizing current. Okay, so flux, here comes the flux pi equal to, due to this AC current there will be sinusoidal flux creation, that is I pi m sine omega t. Okay, so this is the flux due to I mu, which is equal to Im sine omega t. Okay, due to the sinusoidal current flowing through the winding, there is a sinusoidal flux being created in the winding. Now here comes our Faraday's law of electromagnetic induction, EMI. Okay, so what is it saying? It is saying the EMF generated is proportional to rate of change of flux linkage. So this was the definition. This was the mathematical expression for our Faraday's law of electromagnetic induction. Now, so I have to keep a constant to make it equal, that is number of terms on the primary d pi by dt, where n1 is primary terms and E1 is primary induced EMF. Primary induced EMF. E1 is primary induced EMF. Now I am going to substitute this pi value here. I am going to substitute equation 1 into, okay, the flux, AC flux is given as d by dt of flux is pi m sine omega t. Okay, so that will be n1. Actually there will be a minus sign. This is due to Lenz law. Okay, so this is due to Lenz law. So what is this Lenz law is? So let us go back to our transformer. Here what happens is, here E1 is being produced because of V1, right? V1 is the supply and E1 is the EMF induced in the primary. So according to Lenz law, so let me write a statement of Lenz law here. So according to Lenz law, okay, the effect opposes the cause. Okay, effect opposes the cause. This is simple statement for Lenz law. So that means what happening here is, so here E1 is happening just because of flux and flux is happening just because of supply voltage. Okay, that means E1 is indirectly happening just because of V1. So E1 is effect here, E1 is called effect and V1 is the cause to that effect. So according to Lenz law, this effect will oppose this cause. That means E1 is opposing V1. So this is the statement. So generally it is given as V1 equal to minus E1 in phasor diagram, that I am going to explain later. Okay, so for now you need to understand that E1, which is being generated because of V1, opposes the V1 itself. Okay, that means the effect is opposing the very cause which is creating it. Okay, this is Lenz law. Just to make sure that we are going to keep a negative sign, this represents Lenz law. Okay, so E1, which is effect due to rate of change of flux, is opposing the rate of change of flux itself. Okay, so now d by dt of pi m sin omega t will be pi m sin omega t will be cos omega t into omega, because it is with respect to dt. Okay, so now it can be n1 pi 1 omega. Here I am taking the negative sign to cos angle. Okay, that will be cos of omega t, sorry, sin is cos omega t can be written as minus, so that means this here I am converting this sine omega t into, sorry, cos omega t into sine omega t. That will be sine of 90 minus omega t. So can I write like this? Cos omega t, I am replacing them with sine omega t. So this will be in first quadrant. So I am multiplying the sine to the angle, that will be n1 pi 1 omega. So I am multiplying this sine, that will be sine of, that will be minus of 90 minus omega t, right? So that will be n1 pi 1 omega sine of, this will be omega t minus 90 degrees. Now if you observe this, you can simply understand Lenz's law here itself. Okay, so here, so here is the voltage expression. This is E1 is induced EMF in the primary winding, right? This is induced EMF in primary winding, right? This is the induced EMF in the primary winding. Now this E1 will be maximum, okay, when the omega t angle is pi. That is, E1 will be maximum at omega t equal to pi. So there is, when we substitute omega t equal to pi, that will be sine pi minus pi by 2. 90 is pi by 2, right? Because pi is 180, pi by 2 will be 90. Okay, so E1 will be maximum at omega t equal to pi. So that will be n1 pi 1 omega sine omega t can be replaced with pi minus 90 is nothing but pi by 2, which equal to n1 pi 1 omega sine pi minus pi by 2 will be sine pi by 2, where sine pi by 2 is sine 90 is 1, to n1 pi omega. This is maximum value of induced EMF in the primary in volts. But we need RMS value. So even RMS can be obtained by maximum value by root 2, that we already know, right? E max by root 2, right? That is n1 pi omega by root 2. Okay, so we know that omega equal to 2 pi f, n pi 2 pi into f by root 2. So by simplifying this expression, the E1 can be given as RMS value of induced voltage. RMS value of induced EMF, E1 equal to 4.44 N1 pi 1 into frequency F. Okay, so this is the expression for RMS value of induced EMF, right? E1 equal to induced EMF and primary, induced EMF on primary winding, N1 is primary terms, and pi 1 equal to flex, F is frequency of the supply. Okay, so this, and one turn equal to two conductors. This is one thing to remember. Okay, so one turn will have two conductors generally. This is considered to be one turn. This is one conductor, this is another conductor. Okay, this one is another one conductor, this is another conductor. So one turn is having two conductors. This is to be remembered. Now we have obtained the EMF equation of a transformer, which equal to E1 equal to 4.44 N1 pi F. Okay, so similarly we can write the value of E2, that is induced EMF in the, this is RMS value of induced EMF on the primary winding. We can obtain the RMS value of induced EMF on secondary winding. But here the turns will be N2 and flex will be same, right? The turns will be here, the E2 will be 4.44, turns will be N2 and flex will be same due to the primary flex frequency. So this is EMF induced in the secondary winding. Okay, now so let us come back here. So we have applied a voltage of V1, right? And there is a flux due to this V1, that is pi, which equal to pi m. sine omega t. Okay, and here there is a EMF, induced EMF in primary winding, that is E1 equal to N1 pi omega sine of omega t minus 90. So this is what happened so far. Okay, and according to Lenz's law, our supply voltage V1 is being opposed by our generated induced EMF E1, right? So by concluding, I can say that here we can draw the phasor diagram of these phases. Okay, so first I am applying voltage V here. So let me draw voltage phasor. Okay, I am drawing voltage phasor. So this is my reference voltage phasor, first V1. Okay, then the flex pi will be lagging this applied voltage by 90 degrees. Okay, because inductive nature of the coil, so the current will lag the voltage first. Okay, so this is, okay, here what happened here, so we are applying voltage and there is a magnetizing current that creating flex which is lagging the supply voltage by 90 degrees because the inductive nature of the coil. So here I mu lags V1 by 90 degrees, right? And flex will be in phase with I mu. Okay, that means here we are going to get the flex here. This is flex being produced in the core material. Now this flex, and here if you observe E1 is having the phase difference of minus 90 with respect to our flex. Flex is sine omega t, but E1 is having minus 90 degrees. That is E1 is lagging pi by 90 degrees. That means this is our flex. So we can represent the lag here. So I'm going to draw E1 here, which is lagging the flex by 90 degrees. So this is our E1. Okay, this is E1 which is lagging the flex by 90 degrees. Okay, so this minus 90 I am mentioning here, this is 90 degrees. Okay, now you can see that V1 and E1 are opposite to each other vectors. Okay, so that I can say V1 equal to minus E1. Okay, so here this is nothing but V1 equal to minus of E1. Okay, so this is vector diagram of a transformer. So this E1 V1 equal to E1 is according to Lenz's law, right? So this is about vector diagram or phasor diagram. This can also be said as vector diagram. We can go deeper into this vector diagram in further classes. Okay. Now let us see the next concept, that is ideal transformer. So let's first see the construction features of a transformer. So we know that a transformer is having a core material, a core, right? So the transformer is having a core and winding is primary and secondary. So mainly these are the parts of a transformer. So the active parts of a transformer are transformer core and transformer winding. So winding is primary and secondary winding. Okay, now let us see the construction features of a transformer. One is transformer core, another is transformer winding. Now let us see the features of transformer core here. Okay, so I have already told you transformer core is a magnetic material, right? Transformer core is a magnetic material. It is made of silicon steel. Okay, it is made of silicon steel. Silicon is the material used to make transformers generally, the transformer cores. Okay, we are talking about transformer core here. Okay, so silicon is the type of material used to make transformer cores, and we know that silicon is a ferromagnetic material. That means it will be having superior magnetic properties. So our core material should allow the flex from primary to secondary freely. So it has to pass the flex from primary to secondary without any resistance. So in magnetic medium, the resistance to flex is called reluctance. Reluctance is called resistance to flow of flex is called reluctance. So in our electric circuits, resistance is called it which opposes the flow of current. But in magnetic medium, reluctance is the resistance to the flow of flex. So resistance to the flow of flex in magnetic medium is called reluctance here. Okay, which is similar to resistance in electric circuits. Okay, now so this ferromagnetic material will be having less reluctance. Okay, because it is ferromagnetic material, so it will be having superior magnetic properties. Okay, and here the transformer core should have high permeability. That means it should permeability means it is similar to conductance. Okay, so that means it should allow maximum amount of flex to pass through it. Permeability is nothing but ability of the core to pass flex through it. Okay, so here the second term we are getting is permeability. Permeability, ability of magnetic material. So I'm writing here permeability. So this is new here. Ability of a magnetic material to pass flux through it. Okay, this is ability similar to conductance in electric medium. Okay, now it has high permeability and low reluctance as I said earlier, and it has low hysteresis loss. So there will be iron losses in transformer. They are iron losses omega iron losses are hysteresis losses and eddy current losses generally. So here we will be getting two losses in transformer. One is hysteresis loss and another is eddy current loss. Okay. So due to the magnetic property, we are getting the hysteresis loss here. Due to the electric property, we are getting eddy current loss. Okay. So by using this silicon high permeability core, we will be getting low hysteresis loss. Okay. The less are the losses, the more will be the efficiency of emission. Okay. By using this silicon steel, we are getting low hysteresis loss. And to reduce eddy current loss here, we are going to laminate the core. The core is laminated to reduce eddy current loss. So what is a lamination? So here, actually this is front view of a core. So if I draw this, the view of a core here, what is a lamination? Lamination means a small sheet. So we are going to cut the core into small sheets and we are going to put them together. That is called staggering. So that will reduce the current flow in the core material because it is also a iron material. Silicon is iron material. Okay, because it is steel material, there will be a flow of eddy currents called eddy currents. So due to that current, there will be a loss, I square R loss, that is called eddy current loss actually. So to reduce the current to flow, to oppose the current to flow, we are going to laminate the sheets and we are going to put some insulation between each and every lamination, so the current will not flow. Okay, so that is nothing but lamination. So here I'm going to make one lamination and I'm going to put another lamination here and next one, and I'm going to combine them and I'm going to press them together to form one core material. So this is nothing but core lamination and core staggering. Okay, so these laminations will be put together, that is called staggering. Okay, so there will be having small laminations and there will be an insulation between each and every lamination, that is to reduce the eddy current losses. Okay, so by using laminations and placing insulation between each and every lamination, we are going to eliminate this loss due to eddy currents, that is called eddy current loss. Okay, so to reduce eddy current loss, we are going to make laminations in the core, that is called core is laminated to reduce eddy current loss. So the type of steel generally used for power transformers. So here there will be two types of transformers. One is power transformer, another is distribution transformer. So power transformer will be mostly step-up transformer, which is used at high voltage levels. Power means it will be having high voltage rating. and distribution transformer will be very low rating transformer, which we see generally in our villages and towns. Okay, so for power transformers, the type of core material used is called CRGO steel. This is one of the most important question in any competitive exam generally asked for electrical engineers, and this one also. The core is laminated to reduce which of the losses, eddy current, hysteresis, iron losses, like that. Eddy current loss is eliminated by laminating the core. Okay, so CRGO steel, CRGO is nothing but cold rolled grain oriented. So by doing some process, we are going to orient the grains in the magnetic material such a way that the permeability of the core material will improve. That process is called cold rail grain orientation. So the process of material which undergo this CRGO is called CRGO steel. The steel that undergo this process is called CRGO steel. So that steel is used for power transformer. And there is another material that is used for distribution transformers that we see in our villages. That is called amorphous steel. So this is the steel material used for core material in distribution transformers. You can see there will be a amorphous written on the transformers. If you ever come across a transformer, distribution transformer, small transformers at any shopping mall or something, so you will see amorphous core is used. Okay, you can see it if you have any choice. Okay, now let us move to the second part in transformer, that is transformer winding. We know there will be two windings, primary and secondary. Okay, so winding is nothing but a conductor. Okay, conductor that allows current to flow through it, current flow. Okay, so generally copper or aluminum are used as conductors. Okay, so for power transformers, copper is used, or aluminum is used for distribution transformers. Okay, and they are not made up of solid single solid conductor. There will be a additional loss due to this solid conductor, but instead they will be stranded. Stranding means, so instead of a solid conductor here, so this is a solid conductor. Okay, so there will be a stranded means there will be a small conductors, and they will be twisted such that, so if you observe any transmission line, the transmission line will be, or any copper wire, if you consider any house wiring equipment, so that copper wire will be having small conductors. They are called strands. Okay, strands. Each one is called one strand. Okay, so this stranding process will reduce some of the losses. That's why the stranded conductors are used for windings in any machine. Okay, now using these stranded conductors, we can reduce one more effect, that is called skin effect in AC transmission. Okay, the skin effect can also be reduced using stranded conductors. Okay, so this is about constructional areas of a transformer. Transformer is mainly having two important parts. So first one is transformer core, and the second one is transformer winding. So here we are going to use silicon steel as transformer core. So for power transformer, CRGO steel is used. For distribution transformer, amorphous steel is used. Okay, because they will be having high permeability, that is ability to pass the flux through it, and low reluctance. Okay, so they will reduce hysteresis loss, and we are going to laminate the core to reduce eddy currents. Okay, so this is about core material. Now coming to windings, copper or aluminum are used. Copper is used for power transformers with high voltage rating, and aluminum is used for small rating transformers, that is called distribution transformer. So windings are not a solid conductors, they are stranded to reduce losses and skin effect. So this is about constructional features of a transformer. Now let us see the ideal transformer. What is a ideal transformer? Hello students, now let us see a ideal transformer. So ideal means there will be no losses generally. So it is not available physically. There will be no ideal transformer or ideal things. Okay. So but we are going to see the behavior of ideal transformer, and we are going to compare this ideal transformer behavior with a practical transformer. Okay. That means we are going to see the property of ideal transformer, and we are going to compare the same with our practical transformers. So there will be losses considered into, and there will be resistances, iron losses. Okay, so we are going to see those parameters for ideal transformer and practical transformer, and we are going to compare the behavior of our practical transformer. So we are going to assume these things for ideal transformer because it won't exist practically. So these all these are assumptions only. So the permeability of transformer core is assumed to be infinity for ideal transformer. Okay, permeability means the ability of a magnetic core to allow magnetic flux to pass through it. So ideally it is infinity, but practically it is not infinity. It will be having some extent. Okay. Now excitation current, that is I mu, I discussed earlier, required to produce flex. This is flex here. This is flex. To produce flex in the core is zero. So there is no need of I mu, that is magnetizing current, to produce flex in a ideal transformer. That means there will be a no need of reactive power, which will save our real power. Reactive power is not required because reactive power is the power required to magnetize any inductive coil. Okay, so if there is no I mu, there will be no reactive power. Okay, that will increase the real power content. Now, the third point is iron losses in transformer core are assumed to be zero because it is ideal transformer. There will be no losses. So, iron losses in a transformer, which are iron losses I earlier mentioned, that is hysteresis loss and eddy current loss. So, these will be zero in an ideal transformer. Resistance of transformer windings are assumed to be zero because we are using copper and aluminum. So, copper and aluminum windings will have their internal small resistance. Okay, in practical machines for ideal transformer, the resistance and inductance are zero. Okay, and magnetic leakage flux in transformer is completely zero. So this is leakage flux is one phenomena which is not being transferred to the secondary core. That means this is a leakage flux. Okay, we know that at primary there is a production of EMF, production of flux. So that flux should pass through the core and that should link with the secondary winding so that the secondary will get some EMF. But some of the flux at the primary will be not flow through the core, it will be just wasted at the primary itself. That is called leakage flux. Okay, so the flux which is not useful, not making any useful work, that is called leakage flux. Okay, the flux not involving in any useful action, any useful action. This is called leakage flux. Okay, so leakage flux is zero in case of ideal transformer. And the sixth point is the magnetization curve of a transformer core is assumed to be linear. So this is one important phenomena. Okay, magnetization curve. What is a magnetization curve? So magnetization curve is nothing but a graph between two parameters. Okay, so I'm drawing here. I'm drawing a graph between two parameters. Okay, so magnetization curve is nothing but a graph between two parameters. That is magnetic flux density B and electric field intensity H. Okay, so that is nothing but, so in simple words, B is nothing but our flux and H is nothing but our magnetization current. Okay, so we know that I mu is required to produce flux. So in an ideal transformer, the curve between pi and I mu is linear. So this one, so this is linear, but practically the curve for practical machines, for practical transformer, it will be called hysteresis curve. It will be like this. It will be something like this. So this is for practical transformer, magnetization curves of a practical transformer, and this is for a ideal transformer. Ideal. That means there will be no concept of saturation in ideal transformer. That means, so this is called saturation here at this point. So this region for practical transformer. So if you from here to here, that means from here to here of current. So let us assume this has 2 amperes of current. This has 4 amperes. So from 2 amperes to 4 amperes, you have increased the excitation current from 2 amperes to 4 amperes, but there is no increase in this flux at this point. That means the core has reached saturation here. This is called saturation region. So if even if you increase the current, I mean excitation current, there will be no increase in the flux. This phenomena is called saturation. Okay, so this happens in a practical machine, but ideal machine there will be no phenomena of saturation. So the as long as you increase the current, excitation current, the flux will increase linear. Okay, so this is the difference between practical and ideal machines. Okay, so for practical machines there is a limit of flux increment with respect to current. Okay, so up to some extent it will be linear and it will be non-linear after some time. It up to some extent is linear, right? After this it will be non-linear. So it is increase, this line is increasing and this is decreasing. So this is not sufficient, this is more than sufficient for you. Okay, so practical machines will be having a saturation problem, but ideal machines will not have any saturation. So the statement here saying the magnetization curve of a transformer core is assumed to be linear means there is no saturation considered into effect on ideal transformer. Okay, so this is about an ideal transformer. Okay, and in this class we have discussed about EMF equation derivation and constructional features of a transformer and what is an ideal transformer. Okay, in the next class we will be discussing about a practical transformer. Okay, thank you.